Hello everyone, and welcome to Why Powders Misbehave, presented by Zachary Cartwright and Mary Galloway. Today's presentation will be about 30 minutes, followed by about 10 minutes of Q&A. If you have a question for Mary or Zachary, type it into the questions pane at any time during the webinar. We'll be keeping track of these to answer during the Q&A, so please don't be shy and submit those questions. We'll also be sending out a link to the on-demand webinar as well as the transcript for you to review as soon as they're available. So without further ado, I'll hand the microphone to Dr. Zachary Cartwright.
Hi everyone, welcome to Why Powders Misbehave. My name is Zachary Cartwright.
And I'm Mary Galloway.
And here we're just going to start with a brief outline of what you can expect today. So we're going to talk a little bit about what powders are, try to give you a definition, and then we're going to focus mainly on three different aspects for powders. We're going to look at physical stability, like caking and clumping and loss of flowability. Mary has some lab data that she will share with us. And then we'll move into chemical stability, thinking about maybe rancidity or browning reactions. I believe you also have some research for us.
I do. We did a study in the lab on degradation of vitamin C.
And then finally, we'll look at some microbial stability. Even though this is a low water activity environment, there's still some microbial concerns. And I believe you were just working on an article or quoted in an article that we'll be focusing on.
Yep.
So Mary, what is a powder? How would you define a powder?
Well, I think a lot of times, and you've mentioned it before, most people know what a powder is in theory because we find them in so many places. When we were discussing this before, market mattered. So when we're talking about in the category of powders, we could have spices, ingredients. The pharmaceutical industry also uses it for excipients and APIs, and they serve a lot of different functions. Basically, a powder is like a small granular product, right? We found a good definition in Ho, Tron, and Bandari from 2017. And just to paraphrase that, it talks about structure as being the main definition of a powder. So amorphous, crystalline, combinations of those two together, depending on and how those interact, and how the particle size will affect the functionality, the application, and the production of the powder. So I think those are really kind of sum up why powders are such a huge market and why they're so difficult, because they span so many different markets and function groups.
And we had spent some time before. We've done a previous webinar on powders, and we dove a little deeper into looking at amorphous and crystalline. And I think basically from a molecular structure, there are some key differences. A crystalline structure will have a repeating structure that's well defined. That's something you can see on a molecular level, and then even visually, you can generally see these differences in powders. And I believe we have some figures for that. And then last time we did talk about mixing these powders and looking at some of the combined effects. So if you are interested in looking more at that, you can look back at our previous webinar. We also talked a little bit about particle size, and I want to hit on that a little bit more. How does particle size affect some of the characteristics of powders?
Yeah, particle size really is a major impact for characteristics in powders and why they can be so difficult. When you have small particle sizes, then you can get a bridging between those particles that you don't anticipate, and then you can start getting them sticky and have agglomeration and things like that. So there are a few things besides just general particle size. You can have particle shape is also a factor too. When you mix, there's been some research too. When you mix crystalline powders together, you will have them what we call deliquesce, which is basically go from a solid to a liquid state earlier than you would anticipate either of the individual powders doing. And the reason is, I think it's because of the having different sizes of particles. Whenever you get these places of contact, you can start having bridging and problems. So crystalline powders can be particularly tricky because, as you said, they have a very ordered structure, and that means that the moisture only adheses essentially to the outside of that structure. It's only a surface interaction, as opposed to with an amorphous, there's a lot of crevices and irregular shapes and sizes, and water can more easily bind with the amorphous. So that does make them functionally different, but it also impacts when you have to use them as a formulator, right? How are they going to go in a production facility?
And last time we talked, we looked at the 5 stages of caking. There's multiple steps to getting to agglomeration and then eventually to liquefaction. And we don't necessarily need to go through them today, but I do want to point out that caking and clumping can start to occur at an early stage. And, one way to control this is by looking at maybe the moisture and the water activity of these powders. And so I thought, we do this in most of our webinars, but it's always really helpful to define what moisture content is and water activity and talk about how we can use these things together to think about physical changes and chemical and microbial stability. So let's start by looking at moisture content and water activity. I know you have a pretty good graphic for this and a good definition. How do you differentiate these two different measurements?
For some of the people we speak to, water activity is a new concept, and most people are very familiar with moisture content. So I like to separate them and say that there's 2 water measurements that we can make. So there's 2 different ones. There's one where we're looking at the amount of water, which is the moisture content, versus the energy of the water. What is the water able to do? And we do measure those in completely different ways. When we look at moisture content, that's a mass percent, so we're just looking at a weight. When we're looking at water activity, we're actually measuring what we call a vapor pressure. So that's similar to what the humidity is coming off of a sample, right? So if you want to kind of look at some of this, our research and some of our other webinars, we talk about water activity. It might be helpful to consider what we're also saying is basically an equilibrated humidity that the sample is putting off. And that might help people understand these 2 things a little bit better. And also how some external and ambient conditions can affect their product, which I think is also something to note and to monitor as well.
And I think it's a good point. I still see it misdefined pretty often, that water activity is sometimes defined as water availability, and that's not exactly the right way. I mean, water activity is a thermodynamic principle. It really is the energy of that water. And it's important to know because the energy of that water can be used for a chemical reaction or texture change or something else. So I think it's really good to really hone in on that point. We are looking at the energy of the water with water activity. And moisture content, if you only look at moisture content, we have clients that come to us all the time who have a really good record of moisture content, but they have a really hard time getting a precise measurement. And because they can't be precise with moisture content, it's really hard to connect some of the problems they're dealing with to moisture content. So moisture content alone isn't going to give you all the information you need, especially for powders. So by combining water activity and moisture content, we can look at the isotherm. And this is something that we always talk a lot about, but it's because it's really a unique way to look at the water in these products and get a complete picture of how the water is behaving in that product. How do you take an isotherm? How do you look at that shape and correlate it to different characteristics of a powder?
Yeah, you can look at, some of the ways that we use isotherms is to define a critical point, a critical water activity, where we're going to start seeing texture changes and other changes within the structure of the product. Basically, at what point does it start to change and take on a lot more moisture, right? And generally, if we're talking about a powder, that is the point where you're going to start seeing caking and clumping. If we have some kind of other product like a snack, it can start getting soft. And so those are really critical points to find out. We can also look at the slope or the shape of the isotherm itself too, and be able to identify the structure, like we talked about amorphous versus crystalline. We can look at that. We can also, by exposing these samples to humid air and basically in real time see how they behave, we can get a lot of really great information about that product that's can be really useful for a client.
And I think it's important to point out that we have a really unique method called a dynamic dew point isotherm. And this is really the best way to get a high resolution graph or picture of how the water is behaving. There are other methods that we'll talk about later, but by using that dynamic dew point isotherm and by using the vapor absorption analyzer, this is really the best way to characterize the water and then to look at some of the factors that we're going to consider, starting with physical stability. So in this next section, let's talk about physical stability and what that means for powders.
Okay.
All right, so let's dive deeper into physical stability. When we think about physical stability in powders, there's really three major factors that we want to consider: moisture, temperature, and time. So I'll let you kind of dive into these and add on as needed.
Yeah, for moisture, basically, if we have more availability of moisture, we're going to have more processes to change, right? More structure to change. When you're talking about the DDI, my first thought was looking at that in terms of like a spray-dried milk powder, where we're going from a glassy state to a rubbery state. Now, if we did a different, more traditional style of isotherm, you actually miss that transition because it's essentially jumps over it, right? You normally kind of hold things at certain humidities and see what happens. But in the DDI, it's the real-time process, and you can actually see these transitions happening. So this is what I specifically am meaning when I'm talking about using the isotherms to be able to see your real-time data and when those critical points start to happen. So moisture is a major impact for those processes because water tends to really speed things up. And so it can be a solvent, it can be a reactant, and it can actually even be a buffer into the chemical reactions. And sometimes the roles change as the process goes along or as more moisture is added to that process, and then you can see different reaction rates actually change. So besides moisture, we can also want to look at temperature. And we do have a graphic that we like to show because it's a really great way to express how that critical point that we've been mentioning will change as we're adding heat or temperature, increasing in temperature to a product. And what happens, and it does make sense when you think about it, is that change happens faster. You're adding energy into the system, and that system, it's flowing faster. So you'll get these changes happen at what would be lower water activities or faster in that process. The last thing is time. If you give a process enough time, it's going to change. So even if you could hold the other things to static, temperature and moisture, if you gave it enough time, it would happen. And I was just thinking the other day about this example. If you've got really old glass windows, and if you were to measure the top and the bottom of very old glass windows, you would know that the bottom is thicker than the top, and that's because they've had a long time to flow. So that's kind of this idea of if you give something a process long enough, it's going to come to completion. All three of those factors will play into physical stability.
And I think it's also important to note, depending on your question, there are different methods or different types of isotherms that you can use. So going back to the dynamic dew point isotherm, you can use this to find that critical point and understand exactly at what water activity or at what relative humidity and temperature combination will cause that effect. And then once you know where that critical point is, then you can also do a DVS test, a dynamic vapor sorption test, to ask the question about time. Right. So going back to your window example, how long is it going to take to actually reach this critical point under a certain condition? And, we have a solution. We have our vapor sorption analyzer that allows you to do both of these methods, which is really unique and really the only instrument capable of doing both of those. So if you have a problem with physical stability, having access to both those types of tests can be really effective. Now let's move a little into your spice mixing project. What was this project? What was the goal of it? And what did you learn from it?
Right. So as we know, moisture will move because we have differences in water activity. So the question is, how much does it move? Can we predict that, and how accurate is the prediction? So we do have a tool. There are definitely equations out there that try to model that interaction between products. And so what we did for our project was essentially that. I think we had 6 different blends. Some spices, we did a maltodextrin and sorbitol, cornstarch and onion salt, and then some spices, sage, oregano, and cumin. We put them together. First, we forced all of them to have a very specific water activity. So, and then we also ran isotherms on all of those ingredients because that is a major factor, not just the starting water activity or a mass ratio in the blend, but what is the characteristics of that isotherm, of how does it behave in the presence of moisture. So we want to know how they take up or don't, or however that might be. We need to know what that information is for that product so we can do a good predictive model. So we did this, and then we mixed them together in known mass ratios. And then we measured to see exactly what the water activity was after we gave them time to equilibrate. And then we also did the prediction. And they were very good. Basically, I'm showing the combinations that we did. The top one there, cornstarch and onion salt. We mixed 1.5 grams of cornstarch, and it started at a water activity of 0.435. And the onion salt, we did it as a gram, but we had it at a lower water activity. So you'll see there that it started at 0.35 water activity. And then we blended this, and our blend actual water activity was 0.429. And when we ran the predicted model that took the isotherms into account, the initial mass, and the initial water activities, we actually predicted that the final water activity would be 0.431. So extremely close. These worked really well. They have really fine particle sizes, actually, so they have a lot of contact, so you're going to get a quicker equilibration. And so that wasn't too much of a surprise, but it was nice that it worked so well. And you can see with some of our other examples that we ran very well. We also did maltodextrin and sorbitol. We varied the amounts. We varied where they started. One was higher than the other one, and then we swapped it. We kind of tried to do various combinations to just test it out a little bit. And then we also did the spices at the bottom, the sage, cumin, and oregano. And those worked quite well. Our worst case scenario in the setup that we did was the very last example. And maybe I shouldn't say that, but the scientist in me says I need to. And you will see that our predicted was 0.35 water activity, where our actual was 0.395. So it was about 0.05 lower. And I just kind of wanted to talk a little bit about how this works and then the comparisons we did. So you'll see here all of the isotherms for the sage, the cumin, the oregano, a combined model, so where we put those all together. And I also wanted to show where we started. This is where we started with all of the ingredients, where the initial water activity, what the initial moisture content was based off of the isotherm and the mass ratios. And once we put it all in there, you can see there that we got a final water activity of 0.349. Now, for this, what's important is we're doing this mathematically. So we want to make sure that we have a good representation, a good mathematical equation and coefficients for each of our ingredients. Once we got that, we got our prediction. It was pretty close. I was pretty happy with that. I think they're just, particle size, perhaps with the spices maybe not having as good a contact. It's possible that once we let them be together longer, we might have had a different, slightly different result. But I was very pleased with the result that we got. I also wanted to take this and look at it the other way. So we modeled the isotherm, as I'm showing here in the red trace, but then I wanted to also compare that with the real isotherm, because after we mixed this blend, we actually ran an isotherm on it to see what we could do. And from there, you can see the differences between the actual isotherm and the modeled isotherm, and they match up very, very well, and especially in the area of interest that we're looking at. So if we're looking around, for spices, maybe 0.2 to 0.4. It's generally kind of where they live in water activity range. You'll notice we have a really nice fit. So I feel very, very good about our data in our study. And this was, like I said, is the worst case that we had. The rest of them actually had much better results. So
I just kind of want to take a step back and think about the real world application of this. I talk to scientists all the time who are under a lot of pressure to get new products out as fast as they can. And if you use this type of modeling for a dry ingredient mix, this is a really fast way to get lots of insights about that final product before you even make it. So it does take maybe a little time to build up a library and have isotherms for each ingredient. But once you do that, then you can sit at your computer and very quickly understand what the equilibrium water activity will be. And with our new program in the moisture analysis toolkit that comes with our vapor absorption analyzer, the toolkit software does all of the work for you. You mentioned those equations, and there are equations in the background, but instead of having to build your own spreadsheet or do this all yourself, all of that labor is being done for you, and it makes it really easy to know what the equilibrium water activity will be. And now you can also get the coefficients for that model that you mentioned. And using those coefficients, you can start to ask questions about, what is the predicted shelf life, or how long will it take to reach a critical water activity, or maybe what type of packaging should I use? And so there's a lot that you can do if you take the time to look at these isotherms and understand exactly, how can I use this data to answer lots of different questions. So I just wanted to point that out, that, the graphs that you're showing do come from the Moisture Analysis Toolkit software. And this is something that a lot of our clients, whether they're making nutritional supplements or, we work with some of the largest spice producers in the country, they're using these equations and using these tools to speed up their production.
Right.
So I just wanted to make sure to point that out.
Yeah, that's a really good point. And I also wanted to add that once you have the isotherms, I can rerun this prediction over and over. I can change any part of it and rerun it in just moments. As an example, I could change the mass ratio if we find that we don't particularly like this blend, or it has we don't like the flowability of it, or something, or maybe the flavor isn't good. Maybe it's got too much cumin in it or something. You could adjust that recipe, right? And you can just do it in the software. Or let's say, as an example, we've talked in prior webinars about the seasonality, how that can change your incoming ingredient water activity. Tends to be higher in the summer and lower in the winter. And so, it's important to monitor what you're getting when it arrives, so you don't get a surprise and moisture coming into your product that you didn't anticipate or want. That's something you could change here. You could change the initial water activity of any of these products and then just rerun the prediction. So once you get that information, you can do a lot with manipulating it.
Well, that was all, mainly related to physical stability. Now let's jump to chemical stability and talk about how we can use water activity to inform or to understand chemical stability better. Moving on to chemical stability, I want to look back at our stability diagram that we had up before. And the reason that this is important, because you have to think about, is your powder delivering maybe the health benefits that were promised? Is the vitamins, are they there that you promised, or has there been some type of chemical change that you need to be aware of? And if you look at that stability diagram, there are different points in that diagram where degradation rates or reaction rates are going to change. For example, around 0.6 water activity, you might have an increase in browning reactions. At very low water activities, this is where we see lipid oxidation start to increase. And so you just need to be aware of how water activity is affecting reaction rates, and maybe which reactions are related to an end of shelf life. So I know that you recently worked on a vitamin C experiment and looking at how it relates to water activity. Can you explain this experiment and what you found?
Yeah, so chemical reaction rates are a little more complicated to track, but if you can track them, and that is doable, to be able to track the reaction rates, we can use that information to predict a shelf life and a timeline, essentially, to when they've reached a point where we'd consider the shelf life ended, right? So our study was on ascorbic acid. And basically, we exposed it to 2 different water activities and 3 different temperatures. And then we tracked how it degraded using UV vis, and we're able to calculate those rates. One of the parts that's critical about this is we were using the Arrhenius equation, which is very common to use for this type of reaction. So basically, you're going to connect a rate to a temperature and an energy, right? So we already know when we talked about energy, we can relate that to water activity specifically. So basically, we run a study where we're starting at time 0, and then over a period of several days to weeks, we've gone and exposed those that ascorbic acid to a specific humidity and temperature, and then we watch it change, and then we can graph it. So this is our study. Essentially, we would like to know how temperature and water activity are going to affect the degradation rate. So we've got these time plots here that we're showing the graph. So we have our water activities were 0.76 and 0.948. Then the temperatures that we used, and we are running this as a little bit of an accelerated study. So we have 30 degrees C, 40 degrees, and 50 degrees C. So essentially, we put this into the calculator, and we use the Arrhenius equation to help draw the information and correlate everything. Once we get all our data in, our study data in, then we can tell the program specifically what our interest is. So what temperature are we interested in? What water activity are we interested in? And then we also need to define in the study where we're going to end shelf life. So what percent is left? And in our case, what we did was we decided that 75% of the vitamin C left would be the end. So we would essentially lose 25% of our vitamin C, and then we would call that the end of shelf life. So like if you're a formulator or a manufacturer, if you have like a vitamin like you were talking about, you have claims for so much, vitamin or the potency of your product. So you would base whatever ended shelf life on that value, right? So once we can put all that information in, then it can calculate a shelf life. So in our case here, with our ascorbic acid, if we were interested at 30 degrees C, and we were going to have it around 0.8 water activity, which is pretty high. A bathroom could be that, though, right? So, which is relevant to about 80% relative humidity. And then, like I said before, the 75% is going to be the end. We would have 62 days before this ascorbic acid was no longer potent enough. So that's basically how the chemical stability works. So we just need to track it. And if you're able to measure that, then you can do this study.
And again, this is another tool that we have in the moisture analysis toolkit that we built specifically for chemical stability. And even though it does take some time to gather data, I mean, I'm sure it took you a while to gather all of the data. But once you have that data collected, it's really easy to graph in the toolkit. And like you just showed, you can put in in a starting water activity, a temperature of interest, and then define what's ending your shelf life and quickly get calculations. So even though it may take some time to set up a study, and these are studies that we can do or we can also guide clients through using humidity chambers, once that data has been collected, there's a lot of flexibility with the calculations and a lot of insights that you can get. And so, we were looking specifically at vitamin C in your case, but this could be really for anything that we can measure, right? Anything that we can assign a value to.
Right. And it goes both directions. So it could be, in this case, this is the degradation, but you could do an increase of something, right? As maybe a browning reaction or something like that increased over time. And then that's what ended shelf life. It was maybe a specific color value. It doesn't really matter as long as you can measure it. So if there's some way you can actually track that change, then you can turn it into a rate and you can get plots like this.
And there's so many nutritional supplements now and so many things are in powdered form that using this type of tool could really help them understand maybe what their water activity target is or shelf life conditions or, what does end their shelf life, what percent of losing a certain vitamin or how can they make that claim that's on their label? How do they know for sure? And this is a really good way to do that.
Right. And again, like the example before, you could, change your interest, right? You could change your temperature and your water activity of interest or even how much you want at the end, right? All of that is just easily to be changed and just reran the prediction.
All right, finally, microbial stability. A lot of powders are going to have a really low water activity. And sometimes people don't, recognize that there can still be a safety concern there. I mean, powders could have a microorganism of concern and it may be safe, but it's not necessarily sterile. And once you rehydrate a powder, if there is a a spore there or a concern, a microorganism of concern, once it's rehydrated, this is when we can start to see some safety issues. I understand that you recently contributed to an article, and I was hoping that you could talk a little bit about what was in that article.
Yeah, and you said it exactly. There is an idea that if you have a low moisture food, that you don't have to worry about microbial growth and you don't need to know about water activity. But there have been many, actually, sadly, recalls on low moisture foods, and where they have had outbreaks of E. coli and salmonella, like in peanut butter or flour or things like that. Baby formula, it's disheartening. And that is exactly the case, is that water activity is an excellent way to limit microbial growth. If you have a water activity below 0.6, nothing will grow, right? Mm-hmm. So that gives kind of a false sense of safety. My product is low, I don't need to worry about it. But water activity is not a kill step, as just what you were saying, which means they still live, they're still in stasis. And so if they are exposed to a higher humidity or higher water activity environment, like if you put flour into cookie dough, which is what you would want to do with it, right? Now you've created an environment where those microorganisms can now grow and proliferate. And you can see where the salmonella or E. coli or whatever is becomes dangerous to the public. So this is actually a really large topic. When I went to a conference on food protection recently, they did discuss this quite a lot, had many sessions on it. And right now there's a lot of research out there too on what can we do to possibly sterilize or pasteurize these low moisture foods. So the research is being done out there, and we know several researchers, mm-hmm. and I know you do as well, that are working on this very actively to try to think of and come up with these ways that we can to not have any microbial growth or these outbreaks that are happening, that we can pasteurize or sterilize these low moisture foods.
Yeah, and one of those researchers we recently talked with is Dr. Jennifer Acuff, and she's looking at low moisture foods and environments that they're produced in, and thinking of different ways or sanitation techniques, or how can we prevent foodborne pathogens from being even in low moisture foods. And so we recently recorded that podcast with her, and that's something that she discussed. And I think just from my point of view, I think just really staying on top of your sanitation and making sure your environment is as clean as possible. And this is something that we also talked recently to Dr. Minto Michael at Washington State University about, again, looking at microbiology and really understanding, there are different temperature, time combinations and water activity. But like you mentioned, you can't heat every type of food because you're going to cause some structural change. So there may be other ways, microwave or high pressure processing or something else that we can use in combination with thinking about water activity to make sure that these foods are as safe as possible. So if you'd like to, you can listen to the podcast with Dr. Acuff or Dr. Michael to learn a little bit more about food safety.
Right. And I also thought of how water activity actually plays a part when you're doing your pasteurization step. So even if you are able to do that, let's say if it's beef jerky or something like that, there is a time temperature combination and a humidity as well, so to make those effective. So that's the other part of it, is that if you're able to do that, are you creating an environment to actually kill the microorganism that you're interested in? So if you do the right time and temperature, but your humidity is low, you're not as effective in sterilization as well. So it's kind of all these factors for mm-hmm. sure.
So as just a brief recap, today we looked at powders. We tried to define them. We looked at physical, chemical, and microbial stability. We talked a little bit about some of the Aqualab products that we use to do your research and inform, what we talked about today. One thing that I did want to mention here that we didn't hit on before is that even though we make solutions that measure final products or measure ingredients, we also have an inline solution called Scala Solo, where we're really focusing on spray-dried products this year. And a lot of powders are made in this way. And so if you're having any difficulties making a consistent product, as the temperature, as the seasons change, we have a solution now that automatically will always help you hit the same water activity for that product, and it's called Scala Solo. So I want to make sure that if you're listening, that you check out the podcast that we mentioned, Water and Food. We also have a YouTube channel. Please make sure to listen and subscribe. And at this point, I think we should just open the floor and take some questions.
Thank you, Dr. Cartwright. So we'll use the next 10 minutes or so to take questions from the audience. And thank you to everybody who sent in questions already. There's still time to submit your questions, so please don't hesitate to submit yours. And we'll try to get to as many as we can before we finish. But if we can't get to yours, don't worry. We do have them recorded, and we'll contact you within a day or so to discuss your question. All right, let's get to it. This first question is asking, is there a way to measure or track the hygroscopicity of the powders I work with?
Yeah, great question. So when it comes to hygroscopicity, we can look at the shape of the isotherm curve. And this is something that we brought up earlier, and we can probably bring up back now. But really, you're looking at the slope of the curves. And in this instance, we're looking at different excipients. And the greater the slope of that curve, the higher the hygroscopicity. And the more that specific powder is picking up or absorbing water. So simply from looking at the shape of that curve, we can very quickly and visually see a difference in how hygroscopic those powders are. I don't know if there's anything you would add.
Yeah, that is a good explanation of it. So basically, the steeper that slope, the more hygroscopic it is. So, which also can mean it's going to be able to contribute more moisture to your final product, whatever that might be. So that's definitely a factor, is understanding that relationship and how hygroscopic something is.
And I'll just also add that, depending on your formula or depending on your goal or final outcome, you may want something that has a greater slope or not. So it's just going to be product and formula specific, what type of slope you're looking for.
Right. If you want something that is going to increase or maybe bind with the water as you wish, then that is a good way to do it. You can have an ingredient that has a steep slope and it'll take on a lot of moisture and be able to add a lot of moisture to your product. And then you can kind of formulate to the specific water activity you're looking at. But it's not necessarily a bad thing. It's just something to know.
All right, this next question is, what affected vitamin C degradation more, temperature or water activity?
All right, I'll take this one. Water activity was definitely the major factor in the vitamin C degradation, more so than the temperature. And if you were to go back and look at the data, you could also see this for yourself, because if you compare what those reaction rates with only varying the temperature versus when we varied the water activity, it's very clear actually for this one, which is the more important factor, is water activity.
And it's really going to depend on each vitamin specifically, and something that we've actually been talking about recently. But even though vitamin C behaved in this really specific way, you're going to have to look at each vitamin or each active ingredient, whatever you're concerned with. This isn't always going to be the trend. Right. It's not always going to be water activity having a bigger influence. So It really requires doing this type of study in order to understand maybe which one will have the greater impact.
Right, because it could be oxygen. You could have or like vitamin E that's can go rancid. You could track that, and you might have a different response for that. But for vitamin C, it was water activity.
Our next question is, how does water activity or moisture content track with how quickly a powder will dissolve?
It's actually, I'm going to say it's not necessarily water activity or moisture content per se. It's more about the structure of the powder itself and how quickly it can dissolve. And what's the environment that powder is going to be in. If it's like a drink mix, then it is going to be in a high water activity atmosphere environment so that it'll dissolve quickly. But it depends. As an example, if you have something that has a hydrate, generally it's already got water bound to it that tends to dissolve quicker. So it all kind of depends. It's not as simple as knowing the water activity and moisture content of a powder. It's more about the structure and how that can quickly dissolve.
And I'll add that maybe by also looking at the isotherm and looking at a DVS test, if you're able to identify a deliquescence point or a point where everything goes into solution, then we can use a DVS test to understand, how long is this going to take. So maybe looking at the structure and then also being informed by the isotherm as well.
Right, because you could have that is an important part of a powder, is having it dissolve, because most of the powders we experienced are supposed to do that, right? If you just have a drink mix or a powder, that you're going to add it to something else. But what if you want to prevent it to cake and clump before, like, it's in the package? And I think we've all experienced that, or we've had a drink mix or something and it's like hard. So maybe, we looked at the isotherm, we'll figure out what is that critical point for that mix, and then make sure we have packaging that ensures it doesn't go above it, or maybe we need to add a anti-caking agent or something like that. So those all kind of factor into the dissolvability of a powder.
All right, it looks like we're close to the end of our time, so we will take one last question, and it will be, how does the shelf life of amorphous powder compare to the shelf life of crystalline powder?
Yeah, it's really going to depend on what is ending the shelf life. Are we looking at a texture change or a chemical change? So first we'd have to define, what does that end point look like? And then what would you add to that?
Yeah, that's a good question. With crystalline powders, they have a deliquescence point, which I mentioned, I know. Again, going from a solid right to a liquid state, and that depends on like the humidity they're exposed to, right? So if you're able to keep the environment around that crystalline powder below that point, then it can change water activity really rapidly and not change the structure of the powder. So you can have really, really long shelf life. You can think of like sucrose or NaCl or something like that, right? So you just have a really long shelf life with that. But if it's above it, then you've got trouble, right? So it all matters on, like you said, what is going to end shelf life, what is the environment it's going to be exposed to, and then what makes sense. We did also a webinar on sweeteners, and so that was an interesting part about sweeteners and their characteristics of when their dissolvability, and we're switching between amorphous and crystalline structures, and how that could, precipitate essentially out of a product at all. It's kind of a complicated question. So is there a defined answer? Maybe I'll just try to simplify it. Crystalline structures, if you can keep it below that critical point, you can expose it to anything below that, and really it's not going to change, because every water interaction is all like surface. But then again, if it's above that, or if it's a chemical reaction, or if it's something else, then it's another thing we need to talk about.
And I'll just add that for crystalline solids or powders, their deliquescence points are usually pretty high, maybe 0.9 water activity or somewhere in that range, whereas an amorphous powder may have a physical change 0.3 to 0.6 water activity. So if it's on texture alone, if that is going to determine a shelf life, then I would imagine that most crystalline solids will have a longer shelf life. But if it's a chemical stability or chemical reaction that we're concerned with, is going to take a deeper dive and an experiment to really answer that question.
Right. And then back with the other crystalline thing that we didn't mention as well, is that if we have small particle sizes, or we have, odd structures or shapes or various sizes, it can really impact where you'll start getting that bridging that is as a surprise at room humidity. So even saying that crystalline, if you keep it below the deliquescence point, that you're free, it also, like, particle size would also definitely impact the stability of that crystalline structure.
All right, that wraps it up. Thank you for joining us today. We hoped you enjoyed this discussion as much as we did, and thank you again for such great questions. Please consider answering the short 3-question survey that will appear after this webinar. Look for the recording of today's presentation in your email, and stay tuned for future METER Food webinars. Have a great day.